All right, so in this video, we're going to talk about quadric surfaces and cylinders. And you'll notice that the way I approach this is a very intuitive way that avoids having to memorize a bunch of unnecessary things. And so we'll start here by just considering an x squared plus y squared equals a squared. And if I were to ask you what's that the graph of, generally most people will say, well, that's a circle centered at 0, 0 with radius a. And while you're not wrong, I don't know that I did a very good job of asking you the question, because in R2, your answer would have been right. In R2, that would have been a circle centered at 0, 0 with radius a. But what about in R3? Well, in R3, notice how there's no z in that equation. And you've heard me say this before. If you're missing a variable, that means there's no rule on it, which means it can do whatever it wants to do. It's unrestricted. So in the xy plane, we do have that circle centered at 0, 0, radius a, but z, being now unrestricted, gives us a cylinder. And so, again, you got to be a little bit careful as to what dimension you're working in, but the big takeaway from this that I want to point out is that we can also be given stuff in R3 and still walk it back to R2. And knowing what we know in R2 as well as we do, that might be enough then to allow us to almost reverse engineer these three-dimensional quadric surfaces. And you'll see me do that a lot in these next few examples. Now, a quadric surface, just in short, is a graph or a surface, if you will, that is a second-degree equation in x, y, and z. So it's kind of like the quote-unquote quadratic of curves. This is now a degree 2 or a second degree in x, y, and z. So one of the general forms might look something like this: ax squared plus by squared plus cz squared plus dx plus ey plus fz plus h equals 0. And again, this is, you don't need to know anything special about it, but I did want you to see that you've got the x squared, y squared, z squared, and then we just go down by powers there. So they'll be of the form like something like this. We'll manipulate it to make it much nicer, but that is what a quadric surface will essentially start off looking like. Okay, so the first one we're going to look at is called the paraboloid. There's going to be 6 of these, and they're actually outlined, and the book does a really nice job. Page 740, kind of giving you a gallery of these surfaces, so I'd recommend taking a look at that. But we'll take a look at a paraboloid first, and this is the standard form, which you do not need to memorize, and this is the example we're going to look at. So what I do is, as I mentioned before, I try to intuitively think about what happens if I put this in a two-dimensional plane. What kind of trace does it leave behind, and how does that then grow into something in R3? So what I mean by that is, if I let, for example, z equal k, where k is just some constant. Well, in the xy plane, so z is some constant, like a 0, 1, a 2, a 3, whatever. If that's the case, then I'm working in the xy plane in R2, and what I end up with are just a bunch of concentric circles. I would have a point if z is 0. I'd have a circle, a bigger circle, and a bigger circle, depending on what k was. All right, so now that's letting z equal k. I'm going to go a step further, and let's let x equal k. If x equals k, then what we're going to have is z equals y squared plus k. Okay? Now, think about that. I'm now in the zy plane, so I'm going to sketch that. And I am going to label things accordingly. This is going to be a y-axis and a z-axis. And if you think about what you're dealing with now, this is going to be a parabola shifted up k units. Okay? And I should go off and say here that this technically would be a k squared. Since x is equal to k, we're going to have our k squared right there, which is important because it's going to stay positive. But you'll have a bunch of parabolas now that are shifted up. So you'll have this one if k is equal to 0. You'll have this one if k is equal to 1, etc., etc. So a bunch of those parabolas. Similarly, and finally, if I let y equal k, Now I'm going to be looking at z equals x squared plus k squared, working now in the xz plane, and once again I'm still looking at those parabolas. Same idea, but notice the way that I label the axes. You can't really see that there as well, but the way I label those axes, that's going to be important and very telling in how this thing works. So now I'd want to put all this together. So I'm going to take my x, y, z space, make a quick observation here if you haven't picked up on it already. Z, because is equal to x squared plus y squared, z is always bigger or equal 0 in this particular case. So z equaling 0 is going to mean that our surface is entirely above the xy plane except for that one little point where it touches. The other thing that I want to point out is this guy right here. Remember, if you look at this in R3, the z-axis is coming out at us. So essentially, if we look down the z-axis, we're seeing a bunch of these concentric circles. Okay? So I'm going to have a point there. I'll have a smaller concentric circle, and then a little bigger one, and then a bigger one, and then a bigger one, something like that, as z gets bigger, of course. And so then, as I look down the x-axis, I should be seeing parabolas, and if I look down the y-axis, I should be seeing parabolas as well. And that's a little bit harder to draw, and so I'm just going to cut to the chase here and connect these. And as I do this now, you can see that you're ending up with what's called a paraboloid. It kind of looks like a parabola. If we take slices of it, if I take slices and I look down it in that direction, the trace that's being left on the slice or the plane that cuts through it is going to be the parabola. Okay, and again, I know that's difficult to see, but I think that if you look in your text, you'll be able to pick that up a little more easily. But just remember, by us setting x equal to k, z equal to k, y equal to k, those being planes, as we cut those, the traces that they're leaving, the impression that they're leaving would be these parabolas. So there's our paraboloid. All right, so now we'll take a look at the ellipsoid. And here's the standard form for the ellipsoid. This is the example we're going to take a look at, and we'll handle this one pretty similarly. We might not need to go into as much detail because now that we've done one example, this one might be a little bit easier to see. So what I'll do to get started is maybe I'll just consider the xy plane. What trace is it leaving in the xy plane? Well, that's found by letting z equal 0. If we let z equal 0, we get x squared over 36 plus y squared over 9 equals 1. And that would then be your ellipse with a major axis of x. Specifically, we've got a distance there of 6, a minor axis of y with a distance there of 3, and as you can see, it is centered at 0, 0. If I change to z equals a different number, 1, 2, whatever, you can see how it would just change to a different constant, in which case then you would combine with that, and it would snowball from there. So that's the xy plane. In terms of the xz plane, this is where we're going to let y equal 0. So x squared over 36 plus z squared over 4 equals 1. And once again, as I draw this, pay close attention to how the axes are labeled. That's the x, that's the z. If that's the case, then that's a 6 and that's a 2. So we want to pay, again, close attention to how we label these axes. And then finally, we'll move into the yz plane. This is where x is going to equal 0, and we'll have y squared over 9 plus z squared over 4 equals 1. Drawing this in R2 with a y-axis there and a z-axis there, that's going to give us now the ellipse with a 3 and a 2. So as we put all this together, again, I haven't done as many of the concentric ellipses as there would be, but as we put this together, I think it's probably going to be easy enough to see how this thing is elongated. So there's x, there's y, there's z, and you can see we're at a distance of 6 along the x-axis, we're at a distance of 3 along the y-axis, and 2 along the z-axis. So that's going to allow us to have a little bit of depth, if you will. So I'm generally not very good at drawing these, but I'll do my best. So we'll come out here at 6. Let's say that's 6. We'll come around, and it'll continue out, and then it's going to come back through. Maybe I'll call this guy here 3. I'll call this guy here 2, since I'm on the z-axis. And then if we were to look down any of the other axes, you would start to see that in R2 there would be these, draw one maybe like that too, you would see those ellipses inside there. So this guy's destined to look more like a blimp or a rugby ball or something like that. But that's your ellipsoid.